Is it waking up? There it goes. Lecture 10. We're in double digits. Let's get started. So how did the first homework go? Design homework, I guess I should clarify, because it's not the first homework. It's the first design homework. How did that go? Good. Teams is interrupting my announcement slide. Okay. Don't forget we have an exam next week. Review Monday, exam Wednesday, no class on Friday. Today what we're going to do is another design example. I haven't done this before. This is my first time doing this in steel design where we do spreadsheet applications. And so really what what we're doing today isn't super inventive, but I think what it could do is just sort of expand your capabilities in design. And so if you understood the last homework, then what we're about to do today will be pretty straightforward. So, all right, everybody get the code? We all have to wait on him. All right, everybody get the code? Okay, all right. Excuse me. All right, so let's just sort of make sure that we're all clear on our step-by-step process. And by the way, I did fix that little typo right here. That that was supposed to be FU. So what we're going to do is compute our factored load, and then we'll compute these two design parameters. And these design parameters, their only real function is to help us select a trial shape. Once we get to that trial shape, we sort of ignore them and just analyze the section. Okay? When it's all said and done, we summarize our results. Now, I have here that we compute the efficiency. I don't want to say going to skip that step today, but you're going to see how maybe computing the efficiency when you look at the problem this way isn't as relevant, but I'll get to that, okay? Now, these are our limit states that we're going to assess, and so this is going to be what we spend some time spreadsheeting today, as it were. But what I want to do is talk about Excel, okay? Now, like I said at the beginning, I said that most of my design problems, really all of my design problems, are going to be designed such that everybody will arrive at the same answer. So if you did the last homework correctly, we should all get the same answer. But in reality, that's not the case. I mean, you have a whole manual to choose from. So what we're going to do is maybe figure out how we address that. I mean, in reality, you have much more options to choose. That can make things more flexible for you as a designer, but it can make it more challenging to figure out which section you should pick. Ultimately, at the end of the day, what we're doing is a lot of repetitive calculations. Excel loves to do that, okay? So we're going to do that for a design problem today. I should mention, excuse me, 3 sets of formulas that are going to help out quite a bit. First, I know this should go without saying that just needing to use mins and maxes are going to show up quite a bit. The if formula, we are going to use the if formula today. One I am not going to use today is VLOOKUP, but VLOOKUP does work pretty nicely if you want to reference values in the shape database. I'm not going to worry about that today because I have about 30 students in front of me, and every one of them brought their AISC 16th edition steel constructional manual, right? Every one of them brought it with them. That's what I wanted to hear. Okay, so that means you all can help me look up values. Okay. So what I want to do is I want to focus our attention on this problem, which is very much like the problem that you did on the homework, but now I want to look at it a little bit differently. Okay. So let me go to the notebook here. So we're going to do a mixture of some calculations here on the board and some calculations in Excel, mainly just to sort of wrap our head around what it is that we're doing, okay? So let's just sort of start by digesting the problem. So we're going to be selecting a W section to resist a factored load of 560 kips. So right off the bat, I'm not giving you a dead load, I'm not giving you a live load, I'm just saying here's the factored load. It's already been factored. Okay? And I should mention, that will possibly happen throughout the semester, that I'll just give you the factored load because I kind of want to just get to the steel design aspects of the problem. Okay? We're going to be selecting a W section, so we're going to assume A992 steel, which is the most common grade for W shapes. We're going to assume 3/4 inch diameter bolts, and we're going to assume that the member's 20 feet long. Now, like I said in the real world, you're going to have much more of a range to choose from. So on the homework, I think I said, what was it, W12s? So now what we're going to do is select W8s, W10s, W12s, and W14s. A couple things about that. Number one, let's just sort of keep in mind, where do we put tension members in buildings? If tension members in buildings are intended to act as lateral braces for wind, where would we put them? I mean, I'm asking. I'm not, this isn't rhetorical. Where would we put them? Like, where are the braces in this building? Somewhere. So they're on the side, they're in the walls, maybe around the elevator shaft, right? Long story short, they're hidden, right? Architect doesn't want braces right through the classroom. It'd be kind of awkward if I was teaching and there was a big old brace right here, right? So the braces are hidden, okay? So in most practical applications, you're not going to have a W section that's 40 inches deep acting as a tension member brace. That's not going to happen, okay? Maybe in a bridge, like a truss in a bridge, maybe you're going to have deeper sections. But in building applications, the braces are tending to be kind of narrow, okay? So W8, W10, W12, W14, that's about as big as you're going to get, okay? So while I am, again, providing some constraints, I'm opening it up a little bit, and that's kind of the point of this problem, okay? All right, so let's start this problem off how we did the last one. What did we start? What did I name that? Constant values. Okay, so let's do that here. So all right. So let's figure out some constant values that are not going to change as a result of this problem. Okay. So let's start off with these. We know those are constant. Those were given. We know that if that's the case, what do we know about our hole diameter, effective hole diameter? Okay, make sure everybody's awake. Okay. $240 right, for the member length. Okay, sound good? Now I should mention that, all right, hold on. I should mention that step one in any design problem is to compute the factored load, but we were given that load as, what was it, 560? So we don't have to worry about that. And by the way, everything that we see here on the screen, I'm going to sort of double up and put in a spreadsheet. So so don't worry, but we are going to double up that a little bit. Okay. Sound good? So what we're going to do is compute our design parameters. Okay. computer design parameters. So here's how I'm going to approach that. .9 times 50 KSI, that's going to be 45 KSI, right? And then I might need some help with this one. What's that? This should be pretty familiar based on the homework you did that was due today. So, I mean, am I going too fast, or is this all good? Okay. What do we get for this?
36.56.
Okay, so 36.56 KSI. Second? Okay, and so what do we get for this?
13.67.
13.67?
Yeah.
I'm getting a little bit of a different value. I got 15 something. Did I do something wrong?
Oh, sorry. 15.32.
That's why I got 15.32. Did you get that?
Yeah.
Okay. All right. And then we also have our R design. Which is what? That's 3 times 8 is 24, so that's going to be something like that, right? Yes.
The 15.32 should be in.
Oh, you're right. You're right. Yes. As soon as you rose your hand, started talking, I was like, "Yep, you're right. That's square inches." Thank you. Okay. I did this part kind of fast because this part can't go away. Should be familiar. Okay, everybody's good with that? Okay. All right, I'm going to leave this up, make sure everybody's good with this. Okay. Everybody got this? Okay. Okay, let's take a step back. Okay. Now that you all have just done a homework on this, we can probably speak a little bit more specifically. It'll probably be a little easier to do that. Okay. So what do we? All right. Let's ignore Excel for a second, and let's just have a discussion. So, assuming Excel didn't exist, tell me what I do with these two numbers. What do I do?
Check the number.
Say it again. Go ahead.
Check table 1-1.
And do what?
Look for W shapes that fit that.
Okay. Everybody with me on that? So you're going to pick a W shape. But what are you going to do with that W shape? Say it again.
Test it.
You're going to analyze it, right? Okay. So how do you do that? Like, how do you do that? Well, in order to do the analysis, you need certain values for a tension member, right? Now let's be clear, we have a W section connected via the flanges, okay? So this is our problem. So what value, give me a value, if I want to analyze a W section connected by the flanges, what's the value I'm going to need? gonna need, I'll let you start. Am I gonna need the gross area? So in order to analyze it, I'm gonna need a gross area. Give me another property of a W section that I'm gonna need. Well, but, okay, all right, let's talk about that. Am I gonna look up net area? Yes, so maybe what I should say is by inputs, I'm talking about lookups, okay?
Thickness of flange.
The flange thickness, there we go. Okay, what else? X bar. Now hold on. You're talking about X bar for the connection. Let's talk about that. What is that?
Will be for WT.
The Y bar for the equivalent WT. Okay, so that's a lookup. What else?
RX and RY.
Okay, I'm going to need RMIN. Now, for a W section, which one's RMIN? Always.
RY.
RY. I promise you, I'm missing some. What am I missing? And? BF and D. Why do I need BF and D?
Shear factor.
For the shear lag factor, right? I'm going to need BF and D, aren't I? Those are properties I'm going to need to be able to do this problem. Sound good? Okay. Okay. Now, my question is, what do I do with these? Now, I believe you said, what's the property I'm going to need?
That area.
Okay, let's talk about that. All right. Let us assume that for a given W shape, I have these. What is the net area for this problem? I'm asking you. How do I compute it? What's my expression?
8G minus the sum of thickness times effective diameter.
Okay. Okay, but I'm sort of looking for something more specific. Like, we know this is 0 for this problem. I'm asking you, how many holes are there? 4, right? So, and that's going to be TF, right? Like, that's the equation, right there. Let me write that up here. So, AN like, that's an equation. Everybody with me on that? Okay. Now, what do I compute next? What's another thing I need to compute? All right, let's talk about shear lag factor. How many cases for the shear lag factor are there going to be?
2.
Which 2?
2.
Case 2 and case 7. What is case 2?
1 X bar connection over L connection.
And I guess I forgot that up here. What is the connection length for this problem? 8 inches. So this is going to be 1 minus Y bar for the WT over L connection. Is that fair? So let's put that up here. Okay. Now let's talk about U7. How do I do U7? How do I do that?
You define VF and D first.
Well, I've got B, F, and D. Let's assume I have those. So what do I compare?
Compare VF to 2/3 of D. If it's greater than or equal to, U equals
You used a word. You said something greater than. There was a 2-letter word that you used. I think that 2-letter word was if. You said if. Okay? So, are you telling me if BF greater than 2/3 of D, the answer is what?
0.9.
What about if it's not greater than or equal to?
0.85.
Isn't that how the Excel if formula works? If this expression is true, we return a value, otherwise we return another value. So, here's U7. Okay. Now what? What do I do with these two? I want to calculate U. What's U? The what? The maximum. Right? Now, how about this? Let's just see if we can combine things. How do we calculate CPN? Somebody tell me, how do we do that? Like, how have we been doing that up until now?
solve for D is fine.
And then do what?
Take
Take the what? Take the smaller. Right? Which is right? Sound good? By the way, there is one more we do have to do. I'll put this right here. So one, we need to do L over R. And the other, we need to check whether or not it's okay. And don't worry, we'll get to that when we do our calculations. Okay. Let's open up Excel. Okay. Okay. All right. So let's see what we can see. What's up?
Figure out what NSF,
That one's this. This is NSF.
okay.
That is GSY. Okay. All right. So let's. First thing I'm going to do some calculations over here on the side. So what was PU? PU was 60. There's that and that. Is this visible? Can everybody, is this good enough that everybody can see this? Okay. By the way, what was, this was 0.75, or we can say equals 3/4. Now, what should I put in this cell, by the way?
Equals 0.75 plus 1/8.
Thank you. Don't type 7/8. It's a formula. Have it do it for you. Okay? Okay. So I went ahead and just put my member length and my connection length there. I purposefully left that in feet and left that in inches just to make sure we're all on the same page. Let me box some things. Okay. All right, so how did we do this? We said equals that divided by the minimum of that, or, so don't forget, parentheses are probably not, the extra parentheses aren't necessary, but just being careful. And then this times 12 divided by 300. Don't forget the times 12. Okay. Is everybody okay with this? Okay. Sound good? Okay, now let's do some columns here. So we're going to have a series of calculations, and for every shape we're going to have a series of calculations. Let's do our inputs first. So what did we say our inputs were? We said gross area, flame thickness, we said BF and D, right? We said RY, and then we said Y bar for the WT, right? That's what we said were the inputs, right? Okay. So maybe what I'll do is I'll do some formatting here. I'll say, okay. Maybe what I'll do is I'll say, okay, everything that's, I don't know, a blue column, do that one. Everything that's a blue column is a lookup from the manual. That's something we're going to look up. Okay? And we'll do a few different checks, okay, just to make sure we're comfortable with this. Okay? So, by the way, let's go ahead and do this. Okay, so we said we're going to do, which shapes did we say we're going to do? W14, W12, W10, W8, right? That's what we said. Let's start off with W14. Somebody find me the first W14 they can in the manual that satisfies these two. A W14 by 53. So let's put that right here. Okay, now what is its gross area?
15.6.
Okay, what about its flange thickness? Well, let's go ahead and get the inputs first.
0.66.
Okay, what about B sub F?
8.6.
The depth?
15.9.
The RY?
1.92.
And then the Y bar. So we're going to need a Y bar for a WT7.
1.38.
26.5 is it? So what'd you get?
26.5.
1.38?
Yeah.
Everybody else get that? Okay. All right. Everybody with me on this? Now, what calculations are we going to need to do? What are we going to need to do? We're going to need to do AN. We're going to need to do what? U2, U7, and then U. I'm just going down right here. We're going to need to do VPN. Ooh, that is bigger. That's supposed to be 11. Okay. Okay. And then we said we're also going to need to do an L over R check. So we'll call that L over RY. And then an OK check. And since these are calculations, I'm going to change their color. I'm going to make these orange. And I am going to zoom out a little bit. I hope that's okay. If I need to zoom in further, I can. What do you think? Is this good? Okay, and then maybe what we'll do, we'll stick a little title on the top of the table. Something like that. Okay. Is that okay? All right. So what is the net area? How do we do that? Here, I'll zoom in. How do we do the net area calculation? We take the gross area and we subtract 4 times DE times TF. Anybody see a problem with how I've set this calculation up? I need to lock this one, right? I need to lock B8. Everybody remember the keyboard shortcut for that? F4. Does that make sense? 13.29? It should be less than this, right? Okay, what about U2? Y bar for the connection divided by the connection length. And I'm also going to need to lock that value too, right? Is everybody, I'm not going too fast. Everybody with me on this? Everybody good? Okay. All right. U7. Okay, let's take our time with this one. And we'll zoom in a little bit on this. So what did we say? We're going to use the if formula. If that is greater than or equal to 2 over 3 times the depth, then our answer is 0.9, otherwise 0.85. And, yeah, we don't need these parentheses. I'm going to get rid of them. Is this okay? Everybody okay with this? We don't need to lock anything for this formula, do we? And then how do we do U? The maximum of those, right? Okay. All right, I got to zoom out a little bit for VPN. I'm sorry. We're going to do the minimum of 0.9 FYAG. Now, notice this. Watch this. I'm going to box that and box that because those are going to have to be locked, right? The FY and the FU. All right, see what I did? Minimum of 0.9 times FY lock times AG, or 0.75 times FU times the net area times U. And the minimum. Did everybody get the same value I got? Anybody have any observations about this value? Yeah, what was the load again for this problem? So is this section good? Is this a good section? No, right? So this is no good. Okay, we'll get to that here in a bit. But I do want to go ahead and set up the L over R. So L over R, we're going to do that, and we'll lock in our length, and that's our slenderness. Okay. Now, let's talk about this OK formula. What conditions have to be the case for this member to be okay? What's the word you said between those two? You said VPN greater than or equal to AU, and then what was the word? And. Okay. Let's write this up here on the board. Can I erase this stuff up here? Yeah. Okay, all right. Let's erase. Let's watch this over here. So, if. Okay. So, let's just sort of pay attention to what's going on in here, and let's see if we can come up with an Excel formula to check whether or not the section's okay. You said two things have to be true, right? So, I'm going to use what's called the AND function. Okay? And what are the two things that have to be true? VPN has to be greater than or equal to PU, and L over R has to be less than or equal to 300. If these are true, it's okay. Otherwise, it's no good. Right? Now, just so you're aware, in Excel, you have to put quotation marks around letters and formulas. So, let's see if we can do this. So, VPN greater than or equal to PU, lock that in. And that less than or equal to 300, we get an OK or a no good. And that's exactly what we should get, is no good. By the way, there is in Excel an AND formula and an OR formula. So I use them both quite frequently. So if we had done this by hand and we did the W14 by 53, it wouldn't have worked, would it? Interesting. So tell me what to do now. Try another one. What W14 should I try? What's the next one?
The 14 by 61.
Okay. So, tell me some values. What's the gross area?
17.9.
17.9. All right.
0.6. 4, 5.
Okay. This is what? 10?
10. Yeah.
This is also 13.9.
Yeah.
Somebody give me, look up the WT. I'll give you the RY. This is 2.45. What's the WT?
WT 30.5.
30.5, yeah.
Yeah. It will be 1.8.
1.8? I got 1.25. Is mine wrong? The Y bar for a WT?
Yeah, 1.25.
So 30.5, right?
Oh, sorry, 1.25.
Okay. Now, everybody watch up here. Now all I have to do, just drag. It already did the net area, already did the U, this. Is this section good? By observation, it is. In fact, I can go ahead and just drag all these formulas down. Now, Excel's getting a little angry at me right now. Why is it getting angry? Because I don't have any inputs, right? Now, notice how I'm not worrying about an efficiency. Why? Because I'm just going to check all of them and find out which one works, okay? So, I think do you have confidence that we have the lightest W14? The lightest W14.
Yeah.
So what about W12s? What W12 should I use?
W12 is 53.
53. Now, hold on. Let's take a step back. Should I check this?
No,
Why are you saying no?
because you have a W14 at 53 and it doesn't work.
Now, hold on. Okay, hold on. We don't know that's the case. Okay, hold on. I want to address that, okay? You're assuming just because it's lighter, it's not going to work, okay? I'm not saying that's the case, because the W12 by 53 has all these different properties, and you don't know what's going to happen at the end, okay? Let me ask it this way. We have a section that works. How heavy is it? The section that works. 61 pounds per foot. If we have a section that works that's 61 pounds per foot, is there an intrinsic interest in checking a section that's lighter that may work? Yes, because that might save us money, right? So I'm saying let's do it and see what happens, okay? So I'll go ahead and, I've got the values here. So what do we got? We got 15.6, 0.575, 10, 12.1, 2.48, 1.02. So that section works, right? And if you're looking for reasons why, I mean, again, ultimately at the end of the day, look at this. You're saying because it's lighter. Yeah, the capacity dropped. It dropped quite a bit. But the capacity is still higher than 560. Look what happened to the shear lag factor, too. It also went up. So that happens. So I guess, like, this is what I'm asking, right? Did we waste our time checking the W12 by 53? No. Why? Because we found a section that worked and it's lighter than the one we had before. See what I mean? Now, let's try W10s. What's the next W10? What's the lightest W10 that works? W10 by 54. Now, we're going to go ahead and check it, but I guess my question is, is there as much reason to check this one? Because even if it works, it's heavier than this one. You see what I mean? Now, do I think it's a good idea to have multiple options in the design scenario? Yes. You don't know what's going to happen on the supply chain land, so there's no reason not to check it, but just know you have a section that is more optimal. So we're going to go ahead and check it. I've got the values here. This one works too. Okay. How about W8s? Is there a W8 you think is going to work? $58. We'll go ahead and check it, but do we have a lighter option? Yeah, we have a lighter option. So. Okay, so we have several sections that work. What's the answer, though, for this problem for our purposes? 12 by 53. So I'll say and that's going to be our answer. Does that make sense? Notice how efficiency starts meaning less? Because we've literally checked every member there is, you know. What would it matter if the efficiency were a little low in this problem? Would it really matter? What are you going to do with it? I mean, you've got every option available, right? So that's sort of my point when I said, like, I'm skipping the efficiency calc because it doesn't really matter once you start checking everything. Okay. Does that make sense? Okay, I want to mention something about the homework. So, for this problem, you're going to check an angle, not a W section, okay? So, I want you to check the following 4 options, equal leg angles, an L8 by 8, an L6 by 6, an L5 by 5, and an L4 by 4, okay? I want to say 2 things about this. So the first thing is that if you look at okay, let's take a W12 by 53 and a W8 by 58. How do you know which one's lighter? The second number, right? Angles don't have that, okay? But one way you can check is that the shape with the lightest weight will also have the smallest gross area. So whichever shape has the smallest AG will be the one that's the lightest. Okay? The other thing I'll mention is that the structure of your spreadsheet will possibly be a little different. Okay? For example, does case 7 apply here? No, this is an angle. This isn't the W section connected by the flanges. I'm not saying you can't use this spreadsheet as a template, but I would make sure that you're checking it to ensure that you're not just replacing some inputs, right? It's going to be a different spreadsheet a little bit, okay? Just make sure you're following that. Does that sound good? I'll pull up the code. That's all I got, everybody.